Layer-wise training for self-supervised learning on graphs, proposed by Pina and Verónica Vilaplana, addresses the memory and computational challenges associated with end-to-end training of graph neural networks, GNNs, on large graphs. This approach reduces the exponentially growing size of nodes' receptive fields and avoids oversmoothing of representations, common issues in deep GNNs. The authors introduce Layer-wise Regularized Graph Infomax, an algorithm that decouples feature propagation and feature transformation at each convolutional layer to learn node representations. They derive a loss function based on predictive coding, a biologically plausible framework that trains neural networks locally rather than from a global loss function. This approach maximizes the mutual information between output node representations and their propagation through the graph, which will be the input of the next layer. By leveraging the tree-like computational graphs inherent in GNNs, the algorithm utilizes neighborhood sampling strategies to reduce the size of the node's receptive fields without compromising information. Unlike traditional sampling methods, this approach focuses on training every layer of the GNN independently, thereby minimizing memory and computational requirements. The authors evaluate the algorithm on inductive large graphs, demonstrating similar performance to other end-to-end methods with substantially increased efficiency. This enables the training of more sophisticated models on a single device. Moreover, they show that their algorithm avoids the oversmoothing of representations, a common challenge of deep GNNs. The proposed method provides a new perspective on tackling the challenges posed by large graphs, contributing to the advancement of GNNs and enabling researchers to explore deeper architectures and apply them to more complex graph-structured data. Layer-wise Regularized Graph Infomax, or LRGI, is a novel algorithm designed for self-supervised learning on graphs. It builds upon predictive coding concepts and their applications in deep learning, such as contrastive predictive coding, deep Infomax, and greedy Infomax. These frameworks aim to capture invariant features by maximizing mutual information between different parts of the input data. In the context of graph neural networks, or GNNs, efficient sampling strategies are crucial for managing computational complexity and memory footprint when dealing with large graphs. Neighbor sampling, a common approach, reduces space complexity from oxygen mononitride to O, QLL equals 1s. L, where S, L, represents the number of nodes sampled for layer, L. Self-supervised learning techniques on graphs, including contrastive learning methods like Deep Graph Infomax, extend concepts from other domains, such as computer vision, to learn meaningful representations of graph-structured data. The main contribution of this work is the development of LRGI, an extension of regularized graph Infomax that allows for layer-wise training of GNNs. This approach enables efficient fitting of GNNs on large graphs while preserving the performance of end-to-end training. LRGI reduces training time and memory complexities, making it possible to train faster and increase model capacity using a single device. Layer-wise training also helps overcome challenges associated with deep GNNs, such as vanishing gradients and oversmoothing. The authors evaluate the performance and training efficiency of LRGI and discuss limitations and future work in the paper. Layer-wise training for self-supervised learning on graphs involves maximizing the mutual information between node-level and graph-level views by training a graph neural network encoder. This approach targets node-level tasks where only one graph is available, and it constructs negative pairs by applying a random permutation on the node features to obtain alternative graph-level representations. The layer-wise RGI algorithm takes as input node features X, adjacency matrix A, backbone flat, theta, global view function GK, and reconstruction networks, H, L, phi, LL equals 1 and H, L, psi, LL equals 1, with K propagation steps. It initializes U, 0, with node features X and fits layers one after the other, applying RGI to fit each layer, ultimately outputting U, L. Notably, layer-wise RGI does not require a large number of negative samples or random graph transformations, unlike other self-supervised methods. Instead, it leverages the mutual information maximization objective to learn context-aware embeddings, avoiding strong assumptions about the downstream tasks invariance to graph transformations. Regularized Graph Infomax, RGI, is a self-supervised method that trains a graph neural network encoder by propagating embeddings as self-supervision signals via mutual information maximization. The loss function LU consists of three terms: reconstruction error, variance regularization, and covariance regularization. These terms promote context-aware embeddings while preventing the collapse of representations. The layer-wise training approach is theoretically motivated by the need to capture complex dependencies between nodes and graphs, and the layer-wise RGI algorithm is a practical implementation of this approach. This method offers several advantages, including reduced computational requirements and improved performance on node-level tasks. In this section, the authors propose layer-wise training for self-supervised learning on graphs, addressing computational and memory challenges in end-to-end training of graph neural networks. They base their solution on the observation that a GNN encoder can be viewed as a sequence of local aggregation and projection operations, which could be trained locally, layer by layer. The authors extend the predictive coding framework to graphs, suggesting that each inner layer should exhibit expressiveness for the overall network to show this property. The key insight driving this work is the realization that if each layer maximizes the mutual information between its output and the next hop, the network will learn effectively. This is achieved through maximizing the mutual information between node embeddings and their propagation through the graph, as proposed in the Regularized Graph Infomax (RGI) algorithm. By setting k equals 1, the authors adapt RGI to match their objective function, focusing on one-hop neighbors. The proposed Layer-wise Regularized Graph Infomax (LRGI) algorithm trains each layer of a GNN encoder independently using a particular case of RGI. This approach allows for local and global embeddings to be defined for every layer, with local embeddings obtained from the current layer's output and global embeddings calculated using a degree-normalized adjacency matrix. The algorithm employs different weights for the auxiliary reconstruction networks at each layer, which are removed after training. The practical advantages of this approach include computational benefits, particularly in scenarios involving large graphs where batching and sampling are necessary. This method reduces the need for full graph computation and allows for parallelization of the training process. Additionally, the authors suggest that layer-wise training can facilitate the use of deeper GNNs, potentially leading to better performance in various tasks. The layer-wise representation generation and inference (LRGI) method decouples sampled nodes per batch from the depth of the encoder, reducing computational and memory complexities. This is achieved by training each layer to maximize the mutual information between output node representations and the input to the next layer. The approach addresses vanishing gradients through local training of every layer and representation oversmoothing via variance-covariance regularization. Experimental evaluations on graph benchmarks demonstrate LRGI's efficiency in terms of space and time complexity, outperforming state-of-the-art methods. The authors of the research paper evaluate their self-supervised learning algorithm on graphs under an inductive setting, which is closer to real-world scenarios and more challenging than transductive settings. They use four popular graph benchmarks: PPI, Reddit, and OGBN products, with varying sizes and statistics shown in Table 1. To assess the quality of the learned representations, the authors employ the linear evaluation protocol, similar to previous works on self-supervised learning on graphs. They train the encoder on the training node's induced subgraph, then obtain the training node representations and validation and test node embeddings using the entire graph. A linear classifier is fitted and evaluated on the downstream task without backpropagating the gradients through the encoder. The authors use a graph attention network (GAT) architecture with linear skip connections and ELU activation, similar to previous works. The default architecture hyperparameters, such as depth, width, propagation steps, batch size, and sampling factors, are shown in Table 2. Each layer is designed to output a dimensional feature vector divided into 4 heads. The authors present numerical results in Table 3, comparing the performance of their algorithm, LRGI, with state-of-the-art methods under the linear evaluation protocol. LRGI achieves similar performance to state-of-the-art methods and outperforms them on the large-scale OGBN products dataset, despite requiring less computation and memory resources. The authors also analyze the time and memory complexities of their algorithm, comparing it with other methods in Table 4. They show that LRGI has a lower space complexity and training time compared to other methods, making it more efficient for large-scale graph datasets. The paper discusses layer-wise training for self-supervised learning on graphs, focusing on the efficiency and scalability of the method. It presents several tables and graphs to support its claims. Table 3 compares the classification accuracy and microaverage F1 score of different methods on various datasets, showing that the proposed LRGI method outperforms others in some cases. The tables also highlight the space and time complexities of these methods, with LRGI demonstrating the lowest time complexity. The text explains how LRGI reduces the batch complexity by sampling only one-hop neighborhoods, making it faster than other methods. It also discusses the effect of increasing the batch size and removing neighbor sampling on training time, showing that larger batches can significantly reduce training time. Finally, the paper mentions how layer-wise training enables increasing the model's capacity without requiring additional devices. The layer-wise training approach for self-supervised learning on graphs is discussed, focusing on its benefits in terms of computational efficiency and performance. The effects of depth and width on the RGI and LRGI models are analyzed, with LRGI demonstrating better performance and memory efficiency as the model becomes deeper and wider. LRGI's performance improves slightly with depth, avoiding oversmoothing through its layer-wise objective. To quantify oversmoothing, the mean average distance (MAD) measure between neighbor node representations is employed, showing constant MAD values with layer-wise training, avoiding oversmoothing. The paper addresses limitations and future work directions, including the need for an exhaustive hyperparameter search and extending applicability to other contexts. The research continues on self-supervised learning on graphs, focusing on layer-wise training for graph neural networks, GNNs. The authors introduce Layer-wise Regularized Graph Infomax, LRGI, an algorithm designed to overcome computational challenges in training GNNs end-to-end on large graphs. Motivated by neuroscience, LRGI is self-supervised, eliminating the need for exhaustive annotations. This method achieves comparable performance with state-of-the-art methods while being more efficient in terms of space and time complexity, allowing for the training of more sophisticated GNN architectures without computational constraints. Layer-wise training for self-supervised learning on graphs has been explored in various existing works, including graph contrastive learning, variance-invariance covariance regularization, and graph attention networks. Previous research has also investigated graph autoencoders, bootstrap latent variables, and addressed the oversmoothing problems in graph neural networks. The authors implemented their experiments using PyTorch and PyTorch geometric, with hyperparameters set based on existing literature and fine-tuned through a small grid search. The hyperparameters included architectural and mini-batching hyperparameters, training hyperparameters, and loss function hyperparameters. A crucial concept in the author's proposed method is mutual information, MI, between two random variables, which quantifies the shared information between them. The lower bound of MI is derived in terms of the reconstruction error, as shown in equation 4 I U V equals H U V is greater than or equal to H U R U V. Here, H U is the entropy of U, H U V is the conditional entropy of U given V, and R U V is the reconstruction error. This equation is central to the author's Regularized Graph Infomax, RGI, method, which will be discussed further in the paper. Regularized Graph Infomax, RGI, is a self-supervised learning approach for graphs, which leverages a graph neural network, GNN, encoder to maximize the mutual information between local and global node views, U and V, respectively. The primary objective is to learn a representation that can be efficiently fine-tuned for downstream tasks. To achieve this, RGI addresses both the maximization of the entropy of the local views, H, U, and the minimization of the reconstruction error of U given V, R, U, V. The reconstruction error is quantified using a fully connected network, H-phi, which reconstructs the local view UI given the global view V, with a square loss function, LREC, U, V. To prevent representation collapse, RGI regularizes the covariance matrix of the representation space using variance-covariance regularization, similar to Barlow twins and VIC reg. This involves two loss terms: the variance term, LVAR, U, which maximizes the diagonal elements of the covariance matrix C to a desired value, and the covariance minimization term, LCOV, U, which forces the non-diagonal elements of C to be close to zero. The loss function, LU, is a weighted combination of the reconstruction error, variance regularization, and covariance regularization. The weights, λ1, λ2, and λ3, are nonlearnable parameters. To symmetrize the loss function, the approach also applies entropy regularization to the sample covariance of the global views, V, and minimizes the reconstruction error of V given U, with an additional fully connected network, H psi. The final loss function, L, is a combination of the two loss functions, LU and LV, which are optimized jointly during training. The reconstruction networks, H phi and H psi, are ignored during inference. Algorithm 2, referred to as RGI, facilitates layer-wise training for self-supervised learning on graphs. It takes as input node features X, adjacency matrix A backbone function flat, theta, a global view function GK, and reconstruction networks H phi and H psi. The algorithm iteratively updates the parameters until convergence. In each iteration, local views are first obtained by applying the backbone function flat, theta to the node features X and adjacency matrix A, resulting in U subsequently. The global view function GK is applied to U and A, yielding V. The reconstruction networks H phi and H psi are then utilized to reconstruct V from U and U from V, respectively. The covariance matrices CU and CV are computed as the normalized outer products of U and V, respectively. The loss function L is defined as a combination of three terms: LREC, LVAR, and LCOV. LREC measures the reconstruction error between the original and reconstructed views, with parallel dot operator parallel F denoting the Frobenius norm. LVAR encourages the covariance matrices to have diagonal elements close to 1, and LCOV promotes off-diagonal elements close to 0. The loss function L is a weighted sum of these three terms, with hyperparameters λ1, λ2, and λ3 controlling the relative importance of each term. The parameters theta, phi, and psi are updated via backpropagation using the gradients of the loss function L. This process is repeated until convergence, at which point the final representation U is returned.